as we are learning about static electricity here. So static electricity, unlike the electricity in motion, which is electricity in motion also constitutes what is known as current. When electrons are moving through a closed medium, if it is a wire and the electron is moving through this wire connected to a battery, then there is some form of current which is given by I is equal to Q by T, and the unit of current was amperes. And whenever you are talking about something like current, you are always talking about something like a charge. So there are some things which we have found out. These things are like these are the universal truths in the field of electrical engineering. So this has been found and validated from various experiments. So the first truth is that the charge of an electron is always equal to 1.6 into 10 raised to minus 19 coulombs. So this is the first thing, and the charge of a proton is 1.6 into 10 raised to minus 19 coulombs positive. And again, how much electrons is needed to produce 1 coulomb of charge? So the unit of, or the SI unit of charge is equal to coulombs. So the truth is how much electrons you need to produce 1. So it can be simply found mathematically by dividing 1 divided by the number of electrons. So you have what you have is 1.6 into 10 raised to minus 19 coulombs is equal to 1 electrons. So you will take this and divide this like 1 electron is equal to 1 divided by 1.6 into 10 raised to minus 19. So this will give the number of electrons needed for 1 coulomb of charge. So this is needed for, this is the number of electrons needed for 1 coulomb producing 1 coulomb of charge. So that is found close to 6.25 into 10 raised to 18 electrons. And again, some other things which you have found is that when you are dealing with static electricity, so I will just rub this and I will put some new points. The point is that when you are dealing with static electricity, they will have to consider two things. One thing is that the like charges will repel each other. So there is a positive charge here and there is a positive charge, then both of them will move in the opposite direction. If they are free to move, they will exert forces on the opposite direction, they will not attract. Again, if there is a positive charge and if there is a negative charge, then they will exert force towards each other. So there is repulsion here and there is attraction in this case. And the second thing about static electricity is that the force between two charges, point charges are, when you consider the force between two charges, we consider the charges to be point charges while we are defining Coulomb's law. So again, when you are defining Coulomb's law, you consider that the 2 point charges which you are considering is point charges, or they are very small in compared to their distances. So the force is directly proportional to the charges and is inversely proportional to the square of the distance, and the direction of the force can be given by whether both the charges are same, then the direction of the force will be away from the direction on which it is acting, and the direction can be given by the unit vector or the position vector, and that was shown in the previous lecture. And this is how you will define mathematically Coulomb's law, and the unit is Newton for the force, and the constant was like Q1 Q2 divided by R square. So it can be written in a constant form where the value of K was found up to be 1 upon 4 pi epsilon naught. So this epsilon naught is known as the permittivity of free space. So what we are considering here is a very specific case. What we are considering here is to define the Coulomb's law. F is equal to k q1 q2 divided by r square, and what we are considering here is that the k is equal to 1 upon 4 pi epsilon naught. So in this case we are assuming that both the charges are located in free space or vacuum. So epsilon naught is equal to 8.85 into 10 raised to minus 12 farad per meter. So this is a unit of epsilon naught, and this is known as the permittivity of free space. So this is the ease with which the electric field can travel in free space, and whenever you are dealing with some other medium like a gaseous medium or the electric field which is flowing through medium like a mica or an insulator, etc., you would have to consider the permittivity of that material, which is known by a term known as the relative permittivity. So this is the permittivity of that medium with respect to free space, and there is something so known as, so you will have to add epsilon r while you are computing the value of the k in that case. Again, the epsilon naught and epsilon r together is known as something like, so what I just said was that this was your absolute permittivity. So it is epsilon naught into epsilon r, and again you have your relative permittivity, which is a permittivity of the free space, and the value is given by 8.85 into 10 raised to minus 12. And when you are considering for any of the medium which is not free space, like an insulator, like a medium like a mica or a gaseous medium, etc., through which the electric field is passing, then you will consider the specific permittivity of that medium, which is known as a relative permittivity, when the permittivity is given with respect to what is the permittivity at vacuum. So if you are considering the two objects which are two charges on which you want to find the force, or you want to apply the Coulomb's law, or you want to find the electric field, etc., then you will, while computing the value of the k, if you will have to add the epsilon r there, which will be for the relative permittivity, and the absolute permittivity or relative permittivity of free space, permittivity of free space and the relative permittivity together is known as absolute permittivity. So this is something which I wanted to tell. And again, there is something known as the electric field. So electric field can be represented by field lines. So one of the simplest way to represent electric field is that if you have a positive charge, you can say that the electric field will radiate towards the outside of that charge, and it can be shown by the arrows from the moving towards the outside of this charge. If you have a negative charge, the electric field will be towards this charge, and it can be shown by arrows coming towards the charge. So this is one of the ways you can use the electric field lines to represent the electric field. So the electric field, due to the various kinds of different charges, whether the charge is distributed on a line, whether the charge is distributed on a surface, etc., or a cylinder, etc., will be very much different, and there is different ways through which you can find out the electric field using the formulas and computation to find out the exact value of the electric field.